So we'll start by defining what is an alternating series. An alternating series is a series in which the terms are of the form -1 to the nth times some positive sequence a sub n. So let me say that again. It's a summation. It doesn't have to start at 1, so I'm just going to say n equals k to infinity. It doesn't have to start at 1. -1 to the nth. It doesn't actually have to be to the nth. It could be the n plus first. It doesn't really matter, as long as you have something that forces it to pop between negative and positive terms. And then you have some a sub n. By the way, your author will call that b sub n, so I might as well just go ahead and do that right now. And I'll just say where b sub n is not negative. So these terms right here, the b sub n terms, we're going to assume that those are the positive ones, and then the negativity comes from that coefficient. And so if you take a look at this, it might be something like a negative b2 plus b3 minus, oops, that's supposed to be 3, minus b sub 4 plus b sub 5. That's an alternating series. And you can see why we would call it that, right? It alternates between subtraction and addition. Okay. So that's the definition of an alternating series. Very, very nice kind of natural way of thinking of something being alternating. Now let's introduce ourselves to the alternating series test. Now, the alternating series test, I'm not going to prove this one, mainly because it is a bear to prove. It's actually not a fun test to prove. There's not really something that you're going to gain from the proof of it. Oops, sorry, I just hit my microphone. And I also knocked off its axis. Sorry about that. Sorry if that was a loud pop. Anyhow, so the alternating series test, its proof is a little bit of a bear. So I choose to normally not prove it. I think I actually have a proof of it online from years ago. So, and anyhow, but the alternating series test goes like this. Suppose you're given an alternating series. You can see it right here. Again, where b sub n is non-negative. The following two conditions have to be met. If the limit as n goes to infinity of that b sub n, the non-negative part, if that tends to 0, and if your sequence b sub n is eventually decreasing, then the series will converge. That's a really nice test. All you need to do is take a look at this b sub n and focus in on that. When you're handed an alternating series, just focus in on b sub n. If the limit of that b sub n tends to 0, and if you know it's eventually decreasing, which you would think that those are the same statement, but they're not, then the alternating series will converge. Really a super awesome test. Very, very easy to use. A lot of students love it. However, a lot of students also think they can use it to showcase something diverges. This is the one test that will not showcase divergence. So again, warning, this test will not showcase divergence. Again, I'm just going to say it again. The alternating series test never, ever shows divergence. You have to use a different test to show divergence. Alternating series test can only show, if you look at that theorem, it says blah, 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 then the series is convergent. It says nothing about the series being divergent. So be very aware of that. Because I will have students on an exam that will say diverges by the alternating series test. And it's like, nope, there's no such thing. So don't do that. Generally speaking, if it does not converge by the alternating series test, it's divergent by the divergence test. Okay, that's generally speaking the correct phrasing. It diverges by divergence test. So let's see this in action, because seeing this in action is glorious. It's like one of the best tests ever. You almost want to just dive into the homework and knock out every single problem if you can. Also, I should say, even the error estimate on this is super simple. So we'll go ahead and go through those. So determine if the following series is convergent or divergent. Again, want to remind you, we're not asking what is the value of this series. We're just asking, does it converge or does it diverge? I also want to draw your attention to something very important here. Notice that if I had erased all of this, almost all of this black ink right here, we would be looking at the harmonic series. And we know the harmonic series diverges. But this is not the harmonic series. This is an alternating series. It's actually called the alternating harmonic series. So I'll go ahead and write it off to the side. It doesn't actually matter if the series starts at 1 or if the power starts at n plus 1 or n or whatever. That does not matter. It's still called the alternating harmonic series no matter what. So let's go ahead, since we know it's alternating, let's go ahead and use the alternating series test. To use the alternating series test, there's only one condition. To use alternating series test, we only have one condition. That I should say, we have one condition to start using the alternating series test. The only condition that we need to be true to start using the alternating series test is that the series has the form summation -1 to the nth b sub n, where b sub n is greater than or equal to 0. That is the only condition. And if you take a look at this, that is a -1. I know you're going to say, but that's not to the nth. Well, basically is. It's n plus 1. Who cares? Right? It's a -1 to a power. It alternates. And then the rest of it actually is greater than 0. We have the following: -1 to the n plus 1. That's totally okay. The n plus 1 doesn't matter. Times 1 over n. And that 1 over n is greater than or equal to 0. So we're ready to use the alternating series test. Check. So let's go ahead and use it. We'll take that 1 over n, which is we're going to call b sub n, and we're going to take the limit as n tends to infinity. We want to know, is that 0? And obviously it is. There's no craziness here. You can just say that's equal to 0. I can easily see it is, right? Not too bad. So check. That's one of the two conditions to satisfy the alternating series test. The second condition is that we need b sub n to be decreasing. And as I've mentioned in previous lectures, whenever you want to showcase something's decreasing, I get it. The author uses n versus n plus 1, but I much prefer just calling it a function and taking its derivative and making sure the derivative is negative. So f of x equals 1 over x implies f prime of x is negative 1 over x squared, which definitely is negative, which implies f is decreasing, which implies b sub n, which f is based upon, is decreasing. Yay. So we have both conditions met. It is the limit of our sequence, our non-negative sequence, is 0, and that sequence is decreasing. This implies the series converges by alternating series test. Nothing else you need to do. It's one of the easiest tests other than the divergence test. That's obviously the easiest, but alternating series test is the second easiest test, in my opinion. It's just two really quick checks. Does your non-negative sequence tend to zero, and is it decreasing? And like I said, you would think those are the same thing, but they're not. If you do have questions, please ask. I'm totally willing to talk about these and kind of cover these. If you're taking a snapshot, take a snapshot. Please do. All right. The next example in line, each of these kind of progress. Oh, I should say as well. So we have now seen that the harmonic series diverges, but the alternating harmonic series converges. So something about that alternation is very special. It makes it converge to zero fast, basically. So let's progress up. Determine if the following series is convergent or divergent. Use your natural intuition first. When you start looking at problems, whether it's in a homework assignment or a quiz or an exam, really think in terms of exam, elevated level. Always just say, listen, I don't have to stick with what he's teaching in this section. Just remember, you have all of the previous tests that you can use as well. And if you take a look at this alternating, it is technically an alternating series. But if you look at that alternating series, the sequence that it's based upon as n goes to infinity is not zero, right? As n goes to infinity, the arctangent tends to pi over 2. You have to kind of, so a lot of people forget that, but if you graph the arctangent, the tan inverse, it looks like this. Well, I guess I could have drawn it better. Okay. It looks like that, where that output is pi over 2, and this output is a negative pi over 2. So as n goes to infinity, limit as n goes to infinity of -1 to the n plus 1 arctan. Notice I'm including in this statement the alternation, because the reality is this limit going to be 0? Remember, all convergent series require that their limit of their sequence, let's get right here, we require that be 0. If that's not going to be 0 in the long run, then the series will never converge. So this, I happen to know, is non-zero. I don't care if it's finite or infinite. It's just not 0. It's not 0 implies that our original series is divergent. I should even say series here. Implies series is divergent by divergence test. So I don't want you to stick in a rut and just say, oh, you know what? I'm in the alternating series test section, so I should always use the alternating series test. The reality is, if you look at your sequence that your series is based upon, and you say, well, as n gets massive, that does not tend to 0, then you have your answer. If this doesn't tend to 0, the sequence, then the series, the sum of all that, will also not converge. That's by the divergence test. Notice I didn't say it's divergent by the alternating series test, because the alternating series test does not showcase divergence. Okay. So very fast. I just want to put that in there because I think that it is important to every once in a while throw a wrench in the works so that you think outside of the section that you're in. All right, let's step forward just slightly. Here's a terrible looking series. So you're working on an exam, and I ask 8 questions of determine if the series is convergent or divergent, just 8 different ones. And one of them has this -1 to a power. negative 1 to the n minus 3, negative 1 to the n, negative 1 to the n plus 2. It doesn't really matter as long as it's alternating. Okay. And you look at that and you go, well, that sequence that the series is based upon, this sequence right here, oops, it's not highlighting, that sequence right there, that sequence is not positive. It's alternating. It's an alternating sequence. So the series is called an alternating series. So that tells me I'll probably use the alternating series test. Just visualize for a moment, as n goes to infinity, will this tend to 0? And the fact is it will, because the denominator has more power than the numerator. So I'm not even going to dip my toes in the divergence test pool, right? So if you're going to try to use the alternating series test, you're going to let b sub n be the non-alternating factor. The non-alternating factor is the root n over n plus 4. That's non-alternating. All right. And we need to show that the limit tends to 0. So first step, the limit as n tends to infinity of b sub n, which is root n over n plus 4. Well, that's the same thing as if you divide both numerator and denominator by n, the highest power of n, which is n to the first. That would be the limit as n tends to infinity. Dividing the numerator by n, you'll get 1 over root n. Dividing the denominator by n, you'll get 1 plus 4 over n. And as n goes to infinity, you'll get 0 over 1 plus 0, which is 0. Check. Great. So our non-alternating factor, b sub n, is tending to 0. Awesome. Now we need to showcase that this, again, non-alternating factor, b sub n, is decreasing. And again, I just want to reiterate, just because b sub n tends to 0 does not mean it's decreasing. If you don't believe me, think about this. If this were the horizontal axis, I could have something tend to 0 that looks like this. Notice it's not decreasing. Every other term is increasing in value. So there is a good reason why not all sequences that tend to 0 have to be decreasing sequences. I'll leave that on there if people are taking pictures or something. So let's go ahead and see, is b sub n decreasing? Because that's the other piece we need. And to do so, to showcase that it is decreasing, we need to transform it into a function and then take its derivative. This is the perfect case of, or reason, justification, I guess, as to why I don't do what the author does. We're going to let f of x equal root x over x plus 4. If you were to try to do what the author does, which is he trades out n's for n plus 1, and then he compares the fractions, it gets very challenging in this case. So it's much better to just call it a function and then take its derivative. Taking the derivative here, derivative of the numerator is 1 over 2 root x times the denominator minus the numerator times the derivative of the denominator, which is just 1, over the denominator squared. Multiply both numerator and denominator by 2 root x. You get x plus 4 minus 2x all over x plus 4 squared times 2 root x. So that's just me multiplying numerator and denominator by 2 root x, and then combine like terms in that numerator. And you get 4 minus x over 2 root x times x plus 4 and quantity squared. Now, if you remember from your Calc 1 class, you had things called critical points or critical numbers. Critical numbers are where your derivative is either 0 or does not exist. So I happen to know the critical numbers here. First of all, X cannot be 0. I should say our critical numbers are X equals 0, really. X equals 0. From the numerator, X equals 4. And if you take a look in there, you might say, but X can also not equal -4. And it is true, it can't equal -4, but it's not ever going to be a -4 for 2 reasons. The first is your summation starts at 0. So it's never going to be -4. But also, it can't be -4 because you're taking the square root of X. So that's another reason why that's not a critical number. So you draw a number line here. Here's 0, here's 4, and then you test your derivative in those intervals. For example, at X equals 1, the derivative f prime will be positive, so your function is increasing initially. But then when you try X equals 1,000,000,000, which is beyond 4, I hope you know, then 4 minus that is negative, but downstairs everything is still positive, and so your derivative is negative and your function is decreasing. So I know that my function is eventually decreasing, and that's all I require pretty much for all series or sequences, is that things eventually happen. And so in this case, we know our function or our sequence will eventually be decreasing. So B sub n, say this implies B sub n is decreasing. If I said increasing, I meant decreasing for n greater than 4. So we have already shown our sequence, our non-alternating factor sequence, tends to 0, and it is eventually decreasing. Hence, the series up there, highlighted, well, not the whole thing, now it's highlighted, that will converge by the alternating series test. So let me write that down. This implies, I'll even write the series here. Series n equals 0 to infinity of -1 to the n minus 3 of root n over n plus 4. Was that what it was? Yeah. Converges by the alternating series test. Super duper nice test. It's really neat, actually. Just remember that alternating series test will never show divergence, only shows convergence. It can only be used if your series is actually alternating. So don't try to use it if it's not. It's not applicable. Yeah, that's all. So if you do have questions on that, feel free to ask. I'll take a breather and actually drink my shake here. All right. So let's go ahead and, if you don't have any questions, pop forward. Now, I had mentioned in the last class that these types of series right here, where you have like an n factorial, stuff like that, those can be really tricky. I mean, really, really tricky. So again, I like to sneak them in the lectures because I think that it's just worth your while to see them over and over again. Let's just zoom in quite a bit here and consider this series that we're being asked to deal with. Let's conjecture whether or not this series will converge or diverge. Think about that numerator. It's n times n times n times n times n, and it does that n times. The denominator is not n times n times n. The denominator is actually less than that. The denominator is n times 1 less than n times 2 less than n times 3 less than n. So that denominator is definitely less than that numerator. If you think about it that way, it should make sense that we should conjecture this will diverge. That numerator is greater than the denominator. Think about that. If I have a numerator greater than a denominator, like 4/3, and the next term in line is, let's just say, 5/4, and the next term in line is 6/5, and the next term in line is 7/6, and so on and so forth. Even if let's pretend, even if each subsequent term gets smaller, the numerator being greater than the denominator means each term is still greater than 1. And so this is going to be adding numbers, basically, that are greater than 1 over and over again. So the idea here is that this will diverge, but we have to prove it. To prove that this diverges, let's just go ahead and showcase it this way. I'm going to just say note that n to the nth over n factorial. Let's see if I can do it this way. Well, that's equal to n times n. I like to do it the same way, basically, that I did the other day, although this is slightly different. The other day we had n factorial over n to the nth. Today we have its reciprocal. So we have n times n times n times n times n, and this is done n times. In the denominator, we have n times n minus 1 times n minus 2, dot, 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 all the way down to, actually, let's go ahead and do this. All the way down to 2 and then 1. There we go. And by the way, downstairs, if you count 1, 2, 3, 4, and so on and so forth, there are n factors here. So there are n factors in the numerator, n factors in the denominator, so we can break them into n fractions. N over n over n minus 1, n over n minus 2, dot, 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 n over 2, n over 1. I hope that makes sense, right? And let's see. It's 1. It's greater than 1. It's greater than 1. It's greater than 1. Yeah, okay. So notice that I'm going to use a different ink here. Notice that this right here is greater than 1. Think about just plug in any number of n that you want. 10, right? That's 10 over 9. It's greater than 1. And this one right here, definitely greater than 1 as well. And so on and so forth. This is definitely greater than 1 as well, actually. And so is this. Okay. So we could say that this is greater than 1 times 1 times 1 times dot, dot, dot times 1. So this tells me that this series is going to diverge, because this means that you have n to the nth over n factorial is greater than 1, which implies that the limit as n goes to infinity of n to the nth over n factorial is greater than the limit as n goes to infinity of 1, which is 1, which is not 0. That is, our sequence that our series is based upon is not going to tend to 0. And again, we have divergence by the divergence test. So thus, the series, even though it's alternating, that alternation doesn't matter if the series itself does not tend to 0. It's n to the negative 1 to the nth, n to the nth over n factorial, diverges by the divergence test. So I snuck 2 divergence test examples in here because I just think that, always looking out for that is incredibly important. And it's super easy. If I can use divergence test, I will, hands down. Now, let me zoom out. There we go. Some people like to take snapshots, so that's okay. Now, there were some problems on the homework. I was getting emails from students like, what am I supposed to do in this situation, right? There were some problems on the homework that would say stuff like, find the value of p for which this series converges. So I put one of those in this lecture because, well, I just thought it would be nice to reinforce that idea. For what values of p is this series convergent? This is not asking for what values of n. n is just the index right here. N is running off to infinity. What we're being asked here is there a condition that has to exist on P so that it forces this to be convergent? Well, you can see right now what kind of series it is. It is an alternating series. And if you think about all the tests that you have, all of them require your series terms to be positive, except for two. If it's geometric, which this is definitely not geometric because not all the stuff is raised to the power n, and if it's alternating. If you have an alternating series, then, I should say, if you have terms that are not negative, then hopefully it's an alternating series. And this it's -1 to the n plus first. So it's alternating. So we require, maybe I should write it this way, for convergence, we require one, that the limit as n tends to infinity of the non-alternating factor, which is going to be the natural log of n to the pth power divided by n, we require that to be 0. And 2, we require that the non-alternating factor, which is the natural log of n raised to the p over n, is eventually decreasing. By the alternating series test, that would force this, or that would state that this series is convergent. So let's go ahead and figure out what are the conditions on P to make these statements true. Let's go ahead and start with number 1 up there. So we'll take the limit as n tends to infinity of the natural log of n raised to the p power over n. Now, as n tends to infinity, that is going to, if p is, we'll start with if p is 0. If p is 0, actually, that's fine. So if, condition A, if p is equal to 0, we have the following. Limit as n tends to infinity of the natural log of I don't care to the 0th power. Because anything to the 0th power, well, any non-zero thing to the 0th power is going to be 1. And that will be 0. So that would work if p is 0. Now, obviously, I don't want to go through every single power in the universe like that, but p equals 0 was kind of the linchpin. That was the one that I had to start with. Now, think about it. If p is positive, we have the limit as n tends to infinity of the natural log of n to the pth power over n. And that, if p is positive, is going to be infinity over infinity, right? Because n's running off to infinity, and you have a positive number, somewhat large, raised to a positive power, that's going to tend to infinity. So we have infinity over infinity in this case. And so you'd have to use L'Hopital's rule. So let's go ahead and do that. So let me just use green. This tends to infinity. This tends to infinity. So let's go ahead and use L'Hopital's rule here. Via L'Hopital's rule, this will be the limit as n runs off to infinity. The derivative of something to the pth power is p times that something to the p minus first power. The derivative, and then times by the chain rule, the derivative of its argument, which is the natural log. You take the derivative of the natural log, it's 1 over n. And then take the derivative of that denominator. Something interesting happens, right? So this is a really fun I think, a fun and interesting problem because this turns into the natural log, I'm sorry, p, I'll move the p out front, times the limit as n goes to infinity of the natural log of n to now the p minus first power all over n. And notice that this is actually the same problem as before. It's just, well, the p minus first power instead of the pth power, right? So again, you would use L'Hopital's rule because it's infinity over infinity. And if you use L'Hopital's rule again, you get p times p minus 1 limit as n goes to infinity of the natural log of n to the p minus 2 over n again, because it's going to be the same exact derivative as above. The only change between here and what you had previously is that the power will be p minus second power and a p minus 1 will be brought out front. And you could do this all day long until you get rid of all powers of p. Okay. If p is an integer, this will eventually limit out. Let's say that p is 3, 2, or let's say the p is 2 actually. 2, 1, yeah, that would be eventually 0. So equals ... equals 0. That's if p is an integer. Now, again, we're assuming that p is positive, right? If p as a power is an integer, then you can imagine, just pretend for a moment that we had started with the integer of p being 2. This would be 2 times 1, and this power right here would be the 0th power, which means that you're taking the limit as n goes to infinity of 1 over n, which will be 0. That's why I'm telling you that eventually, if p is an integer, that will end up being 0. Okay. If, on the other hand, let's just pretend p was not an integer, I want to again convince you that this will end up being 0. Why? So if p is an integer, we've done that. If p is not an integer, it'll still converge. Why? Because pretend for a moment that the original power was not an integer. It's still positive, but let's just pretend it's not an integer. Let's pretend as though the original power was 3/2. Well, then this would be a 1/2, right? And this would be a negative 1/2. In other words, even if it's not an integer power, eventually I'm going to get a negative exponent on this. And once I do, let me scroll down a little bit to show you. Once I do get a negative exponent on that, it ends up being something like this: 1 over n times the natural log of n raised to that 1/2 power now. Well, as n goes to infinity, that's 0. So whether it's an integer or a non-integer positive number, it will always tend to 0 eventually, because you're using L'Hopital's rule over and over and over again until that either pops downstairs or the power becomes 0, one or the other. The reality is, at that point, the limit will be 0. So we have that if p is greater than 0, the limit will be 0. So again, limit is 0. If p is equal to 0, the limit will be 0 if p is greater than 0. And now we'll do the last one. What if p were negative? Well, if p were negative, that's actually the easiest of all. Because then we would have the limit as n goes to infinity of the natural log of n to the pth power over n. Is that what it was? Yeah. But because p is negative, that will actually go downstairs. You have to kind of visualize that with me. But the reality is that because p is a negative number, that natural log would just pop downstairs, and as n goes to infinity, that would be 0 immediately. No question. It just jumps downstairs. You have infinity times infinity downstairs, 1 over it. And so that would tend to 0. And so in all 3 possibilities, I know the limit's going to be 0. All right. So by the way, that was A, B, and C. So our first thing we needed to do was showcase that, or find out the powers of P that would force that limit to be 0. And we found out that no matter what the power of P is, that limit will be 0. So this is 0 for all powers of P. The other thing we need, so I'm going to put a little check mark there. The other thing we need to showcase is that this sequence is eventually decreasing. Okay, well, let's go ahead and transform that into a function. Now, this might be a little bit of a nasty process, but let's just see what happens. So part 2, you're probably thinking, wait, wasn't the previous step the nasty process, right? So we're going to let f of x equal the natural log of x raised to the p power over x. And I want to showcase that that is decreasing. So I need to take its derivative, f prime of x. Well, that is going to be, by the quotient rule, p times the natural log of x raised to p minus 1 times 1 over x, because by the chain rule, and then multiply that by the denominator, minus the numerator times the derivative of the denominator, which is just 1, over the derivative squared. Now, if you take a look at this, these x's cancel beautifully, and I can factor out a natural log of x to the p minus 1. So that's what I'm going to do here. I'll just write, well, yeah, do it this way. Natural log of x to the p minus first power. And when you factor that out of the numerator, you're left with p minus a natural log of x. Actually, this is not too bad now I'm looking at it, because x is going to infinity, isn't it? So this is positive. X squared is definitely positive. And as long as the natural log of x is greater than p, I should say it this way, as long as p minus the natural log of x is negative, right? If I can force this to be negative here, then I know I have a derivative that will be negative. Well, when does that happen? It happens when the natural log of x is greater than p, or in other words, when x is greater than e to the p power. That is, I happen to know this function will be decreasing. When? After a long period of time, it will start decreasing after e to the p power. So if they gave me a power of p, like, let's pretend as though in this original problem, p was 300. That'd be a ridiculously large power, but let's just pretend. Then I know that sequence will eventually be decreasing after x goes beyond e to the 300th power. It will decrease from that point forward. That's a huge number, but still, it's eventually decreasing. So I'm going to make a mention here. This implies f is eventually decreasing, which implies b sub n. Did I call it b sub n? No, I didn't. So we'll call it natural log of n to the p power over n is eventually, very eventually, decreasing. So we have proven 2 things here. Put a little check mark here. We've proven that the sequence, the non-alternating sequence, will converge for all values of p, and no matter what the value of p is, the natural log of n to the p power over n will eventually decrease. That is, this alternating series will converge for any value of p. Converges for all p by alternating series test. That's pretty good, right? That's uh really nice. It's a very, very robust statement. I know a lot of people would love it if it was just if we were purely computational, right? If we were like, oh, let's just be completely computational this entire time. But the reality is every once in a while we do have to sneak in a little bit of theory and rigor in here. Um, Luckily, for the most part, this is awesome, awesome stuff. Very easy to do. Not this problem. I wouldn't say this problem is easy. I would say this problem is a challenge. So do not get me wrong. I know I've been in your shoes. I totally get it that this problem can be a little bit daunting. But 90% of the problems are not going to be like this. They're going to be like all the previous ones we've done in the section. So I want you to be very aware that it's going to be a very smooth ride for a lot of the homework problems. Now, I do want to do mention one last thing before we end the day. Remember that every test we've had has a remainder estimate theorem. The remainder estimate theorem for the alternating series test is super simple. What is the error had you only added up? So error, if we add up first n terms. So what is that error, or what's a bound for the error is really what the question is. It turns out if you use the alternating series test to showcase that something is convergent, the error is the next term in line. That is awesome. Now, I don't have the time to showcase why here, but I'll create a visual actually over the weekend, and then I'll just show you on Monday. But for right now, let's use it, okay? Because it's nice to be able to have everything at your fingertips so that you can dive into the homework. So let's go ahead and show that the series is convergent. First of all, let's just focus in on this. We're going to showcase this series is convergent. Okay. Well, it's alternating. So let's let b sub n equal n over e to the nth, because that's what n times e to the negative nth is. Notice that the limit as n goes to infinity of n over e to the nth is infinity over infinity. Technically, I should be swapping these out for x's, so I'm going to do that because I'm going to use L'Hopital's rule. It's infinity over infinity. But if you use L'Hopital's rule, it's 1 over e to the x, which tends to 0. So we happen to know the limit as n goes to infinity of our base sequence, n over e to the n, must equal 0. Yay. First half of alternating series test done. What about that second half? Well, let, again, f of x equal x over e to the x, and that will imply f prime of x is equal to derivative of the top times the bottom minus the top times the derivative of the bottom all over the denominator squared. If you take a look at that, you can factor out an e to the x and cancel it with the e to the x downstairs. You'll end up with this. And this is going to be negative for all x greater than 1. So we know that our sequence is decreasing for all n greater than 1. Check. So we have the limit of our sequence is 0 and it's decreasing. It converges by the alternating series test. Implies the summation n equals 1 to infinity of a negative 1 to the n minus first times n e to the negative nth converges by alternating series test. Yay. Got another example in. But then they say, well, now that we've shown that it converges, I really don't want to know what the exact value is, because that would take an infinite amount of time. But I just want to know how to get it accurate to within our summation, accurate to within 0.01. That is, we want the error to be less than 0.01. Remember, I always call that the error. So we want our error to be less than 0.1. We want to add up the first, let's say, 5 terms and hope that that error from the true summation is less than 1/100th. What's beautiful about the alternating series test is, again, if you want to bound the error is always less than the next term in line. So let me just write that here. But this is always less than or equal to b sub n plus 1. B sub n plus 1, remember, b sub n is the non-alternating piece. It's this piece right here. So we just want n plus 1 over e to the n plus 1 to be less than 0.01. And you would solve that. Now, to be honest with you, you cannot solve this without using technology. I'm going to say solve. You cannot solve this without using technology. So I'm just going to showcase how I would solve it. I would say I need n plus 1 to be less than 1/100th times e to the n plus 1. Or in other words, I need 1/100th times e to the n plus 1 minus n minus 1 to be positive. How are you going to do that? Well, you can go over to Desmos in our very last minute here, and you're going to go ahead and graph. Getting that in here. You're going to graph y equals 0.01 e to the x plus 1. Oops. Let me put a parenthesis in there. E to the parenthesis x plus 1 minus x minus 1. And we wanted that to be greater than 0. When does it begin to be greater than 0? At 5.473. So we need n to be greater than 5.473. Remember, n is an integer. So basically, n just must be greater than or equal to 6. So how many terms do we need to add up? 6 terms. 6 terms adding up will allow us to have an accuracy better than 1/100th. We'll have an error less than 1/100th on our summation. So that's how you would do this. Very, very nice. I think most people can appreciate the concept of, or not the concept, but most people can appreciate the ease with which, why wouldn't it be 5? Because if you do 5, then our e to the, what do we have here? E to the 0.01 times e to the 5. No, that's right. When you graph that 0.01 e to the x plus 1 minus x minus 1, we need that specifically to be strictly greater than 0. Well, at 5, it's not. It's less than 0. But at 5.473, it crosses over. And from that point forward, it's going to be greater than 0. So we require it, because n has to be an integer, we require n to be 6 or greater. I know what you're probably thinking, but we're dealing with n plus 1. So shouldn't n be 5? No, it is supposed to be 6, because when we solved that, we found out that the value of n has to be at least 5.473. So the next integer up would be the 6. So you start at 6. So you basically say, I need to add up 6 terms. Yeah. There you go. That's it. All right. So I kept you 2 minutes late. Sorry about that. You guys are free to go. Have a wonderful weekend. I'll be back here in 8 minutes for office hours. Otherwise, have a wonderful weekend and pay attention to the homework due dates. I think one of them changed or is changing in a moment. You do have a quiz today. It starts at 10 and you have until 9 p.m. and I'll post the information when you log in. There we go. Thank you for the reminder. I do have that. Thank you. Thank you. Thank you. Thank you. Thank you. All right. All right, you guys, have a wonderful day. And I'll see you when you pop in for the quiz. Take care. And I'll be back in, like I said,